Welcome to everybody. My name is Rasmus Bro from University of Copenhagen, and we're very happy to have Joan Borràs Ferris. Maybe that's yeah, okay, close enough. Here today. This is actually number two of a talk. Alberto Ferrer gave a talk like a month ago, and this is sort of a follow-up to this, and some of related to the same work, I would say, on causal modeling. Joanne is now in Kensite, which is a consulting company, a spin-off from University of Valencia, the Polytechnical University. And with that, please have a go. If you have questions, just put them in the chat, and I will convey them. Here you are. Go ahead, please.
So, thank you so much for the presentation, and I would like to thank you for inviting me to this webinar, because to be honest, I have watched some of them, and for me now it's a pleasure to be in the other side. And yes, as you said, my name is Joan. I did my PhD in the Technical University of Valencia, where I worked in this topic, in the causal modeling and in the quality by design paradigm. And now I finished this work, and now I launched a new company with some colleagues, which is called Kensite. And for me, it's a pleasure because I can use all these ideas in the company. And before starting, I would like to thank also Daniel Palassi, who was a colleague during my PhD, Carl Duchesne, because I did my postdoc there in Canada under his supervision, and Alberto Ferrer, who was my supervisor during my PhD. So these are the contents of this webinar. First, I will talk a little bit about the quality by design paradigm, then about the causal modeling, and finally, I will talk about the 3 applications where we will use these ideas. So first, the quality by design paradigm. For that, we have to understand that we can summarize a process using the idea of the input variables, where we have, for example, raw material properties and some process variables, and then we have the quality space, the WAL space, which is also called the critical quality attributes. So in the quality by testing paradigm, let's say, we focus only on the quality space. If we want to ensure the quality of our product, we have to test, to check the properties of the quality. But sometimes this is a problem because we cannot test everything, or it's quite expensive, and then because we have to wait until the end of the process. For the reason, another paradigm arises in the pharma industry, which is called the quality by design paradigm. Now, we not focus only on the quality space, but also in the input space. We look at the raw material properties and the process variables. So now we don't have to test everything, and we don't have to test a sample of the quality. We define the quality target of our quality space, and then we look at the space of the quality paradigm, quality by design paradigm, where we have the knowledge space. It consists of everything that we know about the process. Then we have the control space. The control space contains the normal operating ranges, and then we have the design space. The design space is very interesting because it's related to the quality target. This is the multidimensional properties of the raw material properties and the process variables, which guarantee the quality of our process. So now we are interested in defining properly this space, because if we are able to do that, and if we work within this space, there is no need to test everything. We ensure the quality of our product looking at our process, the raw material properties and the process variables. But for that, we need causal models. We need explanatory models. And we can build these models using, for example, first principles or data from a design of experiments. But what is the problem in the Industry 4.0 when we look at the processes? That if we look at the box of the data from DOE or first principle, it's empty. It's quite difficult to find this kind of data or information. So it's difficult to build this kind of explanatory model, which are causal. But otherwise, we have a huge amount of historical data, which is called the so-called happenstance data. But be careful, because we can use this data to build predictive model, which takes into account the association between X and Y, but not the causality from X to Y. So I know that there is a temptation to try to build these explanatory models using historical data, but be careful. According to the warning of the Professor Box, we cannot do that. We cannot infer causality in the original space using historical data. But there is an idea from Jekyll and McGregor where we can do it using the latent variable-based models. So now we are going to see quickly these models. As Professor Rasmus Brod said, there is a webinar Alberto did 2 weeks ago, and he explains very well the idea of these models. Anyway, I'm going to talk only a few minutes about them to remember the main ideas. So these kind of models are, for example, the partial least square regression, which is also called PLS. And to understand this model quickly, here we have a simple example where we have 3 input variables and 3 quality variables. And we build a PLS model using only 2 latent variables. So here we summarize both spaces in only one. So regarding the properties of the PLS, we know that the latent variables are orthogonal to each other, which is very important because now we can move one of them independently from the other one. They respect the correlation structure from the past. So if we have a solution in the latent space, we know that will be feasible because respect this information. And then here we don't not only model the relationship, but also provide a model for both spaces. So taking into account these properties, Jekyll and McGregor explain that it provides uniqueness and causality in the reduced latent space. But what does it mean? It means that if we have a movement in the X space, we will know the movement in the Y space? Of course not, because it means causality in the original space. So what Jekyll and McGregor said that if there is a movement in the latent space, we will expect a movement in both spaces. And we will know that this movement in the latent space will respect the correlation structure from the past. So we are constrained to the latent space. So we talk about the causality through the latent space, through the latent variables. So anyway, I would like to be cautious. For that reason, I would like to use this example from the ladder, which is called the ladder of causality from the Book of Why, which is a very interesting book. According to this book, there is no only one meaning of causality. There are different meanings of causalities. Indeed, there are different degrees of causality. For that reason, they use the idea of the ladder of causality. There are different steps. In the first one, for example, we have the association. There, in fact, there is no causality, only correlation. It's useful for prediction, but not for understanding things. Then we have the causality mean. Here, we can understand how a movement in the X space influences a movement in the Y space. And then, in the last step of the ladder, we have the actual causality. Here we have the scientific knowledge, we have the process understanding. We use first principles. So I would like to be cautious. When I talk about causality through the latent space using historical data, of course, we are not in the actual causality. But I guess that we agree that we have something more than only association. So we are in the middle between association and causality in the original space. We have causality in the latent space, as Alberto explained in the last webinar. And this is the so-called restricted causality. We are restricted, we are constrained to the latent space. So now we are going to see how to use this idea in different applications. The first one is the definition of the raw material design space. And first, I would like to motivate this point. For that, we have the raw material properties, the raw material space. They are input variables. And then we have our quality, our critical quality attribute. So as we saw, once we define the quality target, in that case, we have a lower specification limit, we can use a model. We have to carry out the model inversion to define a window. This window is the raw material design space, the raw material specification. So if we work in this window, we will guarantee the quality to be higher than the lower specification limit. And for that, we need to use an explanatory model. And I'm going to show you how to do it using PLS. If we do that properly, we will be able to reduce the price of the raw material. So again, we have the PLS model. We have now 3 raw material properties and only 1 quality property for an illustrative purpose. So if we define a desired value of the quality property, the lower specification limit, we know that we can use the PLS model to carry out the PLS model inversion, where we have a system of matrix equations. And we have as many equations as y variables, in that case, only 1. And we have as many unknown variables as the latent dimensionality, in that case, 2. So since we have more unknowns than equations, we don't have only 1 solution. We have multiple solutions. It means that there is a space which is called the null space, which guarantees the same value of the quality property. In that case, the lower specification limit. So, and then we can go from the latent space to the raw material space, because the latent space is linking both spaces. So if we want this value, we only have to move along the null space. Now, if this is a lower specification limit, we want the quality to be higher than the lower specification limit. So now there is a multiple space, the yellow one, where this constraint is satisfied. This is the design space, but without uncertainty. Be careful about that, because once we receive a raw material batch, we can project this batch. For example, this one, this blue circle, this is a new batch which is projected. First, we have to take into account the SPE, the square prediction error, to check that this raw material batch is following the correlation structure from the past. If it happens, now we can look at the latent space. And we see that this new batch is indeed in the same null space. So according to the prediction, this prediction will respect this condition because will be equal to the lower specification limit. But we have uncertainty, and we have to be careful because due to the uncertainty, we can define the prediction interval. And sometimes the final quality property will be higher, and other times will be lower. So there is no assurance of quality. So here we propose to take into account the uncertainty. How? We are going to define a new point where the lower prediction interval matches the null space. So if we do that and we take into account the leverage because the uncertainty changes, we can constrain this design space without uncertainty, and we end up defining a new space. This is the design space, the high confidence design space. And in that case, since we are talking about raw material properties, they are our multivariate specifications for the raw material, which are defined in the latent space. And we are going to see this idea in a real case study, where we have 12 raw material properties and only 1 quality property. And we define a lower specification limit. As we saw, we want the quality property to be higher than the lower specification limit. We build a PLS model using 3 latent variables. Here we see the goodness of fit of the model, and we see that we are able to explain quite well what is happening in the quality space using only the raw material information. So this model is modeling the impact of raw materials on the quality. Here we have our score plot. Here we define the null space of the lower specification limit, and we can see the batches we use in the calibration step. The green ones are related to good quality, and the red ones are related to bad quality. So we see that since we have a little bit of uncertainty, more or less the null space is able to discriminate what is bad and what is good. But since we have still uncertainty, it is not able to do it perfectly. So if we define this design space without uncertainty, we see that we are accepting bad batches. I mean, raw material batches which lead to bad quality. So we have to constrain a little bit this space to define the so-called high confidence design space. So now we have two spaces, the green one, where there is assurance of quality. Be careful, because maybe you have checked that we have one batch which was bad. Why? Because we can be wrong. We define this space given a certain confidence level, and we define this certain confidence level. So we assume that sometimes we can be wrong, but we define this level. So here at the end, we have the high confidence in space where there is assurance of quality. And here we can apply the idea of the quality by design, which is called the real-time release. Once we check that this batch is in this area, in this region, there is no need to test our product. We know that there is assurance of quality, of having good quality. So we can accept this batch and there is no need to test it. Then if we are in the yellow area, which is called the warning space, means that if we accept these batches, they will be in an area where the prediction will be higher than the lower specification limit. But due to the uncertainty, we will not be sure about that. So our recommendation is, okay, if you want to accept it, do it, but don't use it, the idea of the real-time release. There you should test. So at the end, we provide a kind of quality by design strategy, where you know what to do according to the batch in the latent space. For example, this high confidence space was defined considering a 90% of confidence level. The user is able to choose the level. And this idea was published in ChemoLab and is open access just in case you want to check it, to read it, and to have more detail about this approach. Now, we are going to see the second application. We have been able to define properly the raw material design space, but we want to enlarge this space. How to do it? So let's motivate this point. We have seen that we are able to define properly the window of the raw material space with guarantee the quality of the final product. So if we accept batches which are within this window, we will expect to get good quality. But what happens if we accept more variability, which is outside this window? So this variability will be transferred to the quality space, and we will get bad quality. So here the idea is that we know that there are other kind of variables which are affecting the quality, which are the process variables. So we are going to see if it's possible to manipulate in a smart way these variables to mitigate the raw material variations, to compensate this variability, and to get at the end good quality. If we are able to do that properly, we will be able to enlarge our raw material design, which will decrease the raw material price. So now we don't have only the raw material properties and the quality properties, but also the manipulated variables. And we are going to use another version of the PLS, which is called the sequential multi-block PLS. I don't want to waste a lot of time explaining this algorithm, but the main idea is that it works as PLS in the sense that models the input space and the white space, but now in the input space, we have different blocks, not only one. What is very crucial, we know the flow sheet of these blocks. We can use our knowledge about the input space, and we can give this knowledge to the algorithm. So now we know that we have first the raw material properties, and then we have the influence of the process variables. So we are going to use this information and we are going to model a PLS model in 2 steps. First, we will model the first latent block, which takes into account the impact of the raw material properties, but also the correlated part of the process variables. Why? Because we don't want, indeed, we cannot infer causality in the process variations which are related to the raw material properties. We can do it in the orthogonal part. And the second latent block is going to model this orthogonal part. It's going to model the orthogonal part of the process to the raw material properties, which is related to the quality. And we are going to use this information to mitigate the raw material variations. So, for example, here we have a latent sequential multi-block PLS model where we have 2 latent variables for the first block, and then we have only one for the orthogonal part. So we can define our high confidence design space in the same way we saw before in PLS. And once we receive a raw material batch, we can project it. And we, for example, in this simple example, we see that the raw material batch is outside. We should reject this raw material batch. So here the idea is, would it be possible to manipulate the orthogonal part, which is orthogonal because this latent variable is orthogonal to the first latent block. So a priori, we are able to do it. So the idea is to manipulate the orthogonal part to enlarge the raw material design space and to be able to accept this raw material batch. Why? Because the process variables have been able to mitigate the raw material properties. And we are going to see it in the same example. We have the same example where we have 2 raw material properties, we have 1 quality properties, but now we have 3 manipulated variables. And we are able to manipulate these variables. So again, we have the same goodness of fit. The first latent block has been able to model the same as we saw before, using 3 latent variables. But now we are going to use 1 extra latent variable. But before that, look at the first model, at the first latent block. Now we are not only modeling the raw material space and the quality space, but also the correlated part of the process. So here we have variability in the X space, in the process variable space, which is related to the raw material property. So we don't want, as I said, use this information. I want to model it in the first latent block, and I will use only the information in the second latent block, which is modeled using only 1 latent variable. So now, using only 1 latent variable, we are able to model a great amount of variability in the process region, which is slightly related to the quality. It makes sense. So now we are going to see if we are able to take advantage of this information, which is modeled by the process, to mitigate the raw material variations. So now we have been able to model this orthogonal part, which is related to the quality. And we are going to see in this example. So now here we see the score plot, but we don't have 2 latent variables. We have the first and second latent variable of the first latent block, and then here we have the orthogonal one. So once, and we have been able to define the design space, we have been able doing the same we did before in PLS. We have the null space, we have the confidence limit. At the end, we define the high confidence design space, the green area. So now once we receive a raw material batch, and we assume that we don't want to move the orthogonal part, we can project it. And we assume that the orthogonal part remains as in the past, on average. So if we do that, if we assume that, we see that the raw material batch is outside. We shouldn't accept it. But look at the orthogonal part. If we are able to move, before that, once we project this raw material batch, we can see the time series, the historical values of the manipulated variables, and we can see the expected value of the process according to the correlated part, because was modeled in the first block of latent variables. So we will expect to have this value of the process variables. Okay, now look at the orthogonal part. If we move along the orthogonal variable, which is orthogonal to the first latent block, we see that there is a multiple area which is within the high confidence space. So if we are able to manipulate this process, we will be able to move this raw material batch from here to there. For example, I'm going to take one point, this blue circle. If we are able to manipulate the process to move from the average part to this part, we will be able to accept this raw material batch because we'll be within the high confidence space where there is assurance of quality. So now we can do what happened in the process. We have to move these variables from the expected part according to the correlation to the orthogonal one, to the new one. And we do that respecting the correlation structure from the past. I mean, I know it. The second and the third variable were highly correlated. So we have to increase both, not only one of them. Because when we make a decision, we do it respecting what happened in the past, respecting all the correlations. So now we are able to accept this raw material batch. So to summarize, if we don't want to move the orthogonal part, here we have our high confidence space, which is the same as we use PLS for the raw material properties. But once we are able to move along the orthogonal part, we are able to enlarge the design space. Because here, this is our design space without improvement. But if we move the orthogonal part, we have to project this green area to the first latent block defined by the first and the second latent variable. And we have this new high confidence design space. We have been able to enlarge design space, and now the same batch is within the design space. So we are able to accept it. So we are able to enlarge this space. This idea has been published in this another paper, also in ChemoLab, and you can read it because it's open access. So just in case you want to go into more detail. And now the last one. We are going to talk about the capacity by design, which is totally aligned with the quality by design paradigm. Here, the problem is a little bit different. Here, we assume that we have different suppliers. For example, we have 3 suppliers, and they provide us raw material. So we want to assess them to see who is the best one. So we can use let's say the conventional capacity by testing paradigm, which means that we accept raw material from all of them, we manufacture this raw material, we test the quality, and we say, okay, so the first one is the best one. Why? Because the quality of the product was better than the other ones. But here we have a problem. We have to manufacture the raw material, and we have to wait until the end of the process, which increases the price of the raw material. But we could use the idea of the capacity by design, aligned with the quality by design, as we saw in this webinar. We define the quality target in the quality space. We define our window, our raw material design space. And now we see if they are able to be within this window or not. How? Asking for the properties, that's all. We don't have to manufacture the raw material properties. We ask, of course, we need the value of the properties they are going to provide us, and we will see if they are good enough or not, and which is the best one. So here we have the design space. It's the same as we saw before, but we have a lower and upper specification limit. We have both lower and upper specification limit. For that reason, we get this kind of cat eye. Then once we receive the properties of different raw material batches from the supplier number 1, we can project them. We have to check the SPE, the square prediction error, and if it's okay, we can project them, and we see that we shouldn't work with the supplier because the supplier is outside the design space. But maybe there is another supplier that we projected and is within, and there is another one and is within. So, and then we can model the normal variability of each one. We assume a multi-normal distribution in the latent space. So we define an area which is called ARMOS, the raw material operating space, And it means that we know where we expect to be given a supplier. So if we work with the supplier number 1, the blue one, we expect to be here in this area. So we shouldn't work because we are outside design space. And then the red, the black one, which is the best one, it's difficult to know. So here we provide an index. We provide an index, which is called the latent space-based multivariate capacity index, to assess them, to provide a value statistic to check which is the best one, the black or the red one. For that, I'm going to show the index in the latent space, what we propose, and the capability index in the univariate space that I guess you are familiar with. Anyway, I'm going to explain both. So here we have our design space, our specifications in the latent space, and in the second one, we have a lower and upper specification limit in a univariate space, for example, for the quality property. So once we receive information of our supplier, we can define the ARMOS, what we saw. It means that we know where we expect to work in the latent space. And then if we want to do it in the quality space, we should manufacture all these batches to check, to test the quality, and we will get the natural variability of the quality. In the latent space, we don't need to do it. And this is very important. Then we can calculate the centroid of the ARMOS and the mean of the natural variability of the quality. Then we can calculate the distance from the mean to the specification limit. We know that in the univariate space, we have only 2 distances, but now in the latent space, we have multiple distances. And which one is the important one for us? Is the minimum one. So in the univariate one, for example, we take the minimum one, and here we take the minimum one considering the statistical distance regarding the covariance matrix of the ARMOS. Why? Because it's the critical one. And then we only have to compare. We have to compare this minimum statistical distance with respect to the normal variability in the same way we do in the univariate one. But here we have a multivariate capability index, which is defined in the latent space. And we don't need to manufacture the raw material batches. We have this information only looking at the raw material properties of our supplier. So now here we have an example to see this idea. It's another one where we have only 8 raw material properties. We have 1 quality properties, and we have information from 2 different suppliers. Regarding the first suppliers, we have information about the quality. Why? Because we have been working with the supplier. But regarding the second one, we don't have anything about the quality because we have never worked with them. We only know information about their raw material properties. And this is a real case study. And here we want the quality to be higher than the lower specification limit. So we are going to build a PLS model using only information from the first supplier because we have information about the why. And we see that this model seems rubbish, maybe, because we are able to explain only a little bit of the variability in the Y space. But if you are used to working with data from real processes, will be normal for you in the same way it's normal for me. When we look at real processes and we look at data which is historical, which don't come from DOE, it's normal to have this goodness of fit, a goodness of prediction, and we have to be able to deal with it. So when we define the design space, looking at the first 2 latent variables, we will see that the warning space, the yellow one, is great, this area. Why? Due to uncertainty. That's all. There is no problem. We know that we have a lot of uncertainty, so we have to constrain a lot our design space. But at the end, the important thing is that we are able to define a space where there is assurance of quality. When you check this space, you know that working there, you will be able to get good quality. And if you work in the warning space, you don't know, and that's all. You will have to test the quality of the final product to be sure that you get good quality. But once you are in the green area, you will be able to apply the idea of the real-time release because you will have been able to guarantee the good quality. Okay, but when we see the capacity index of our supplier, the current one, we see that it's awful. Why? Because the centroid of the ARMOS is outside the design space. We are not able to calculate this index. We have a negative index. To be able to calculate this index, at least the centroid must be within the design space. So here we have two options. The first one, looking for a new supplier, and we did it. And when we did it, we received information of the properties, and we were able to project these raw material properties. And we saw that now this new supplier was much better than the current one. Why? Because the centroid of the ARMOS, here we have the grid points in the background, and they are different batches which were projected. We checked that SPE was okay. And looking at these batches, these gray points, we were able to define the ARMOS, and we were able to define the capacity index. And we see that is higher than 0. We can calculate it, 0.29, and was much better than the current supplier. But what is the problem? That the supplier was more expensive, let's say. So our client was not able to work with them. So they say to us, okay, so now you have to do anything else. We can't do anything regarding what we have. Well, this is important. Here we can calculate not only the capacity index, but also the percentage, because at the end we have the normal distribution, so we can integrate this function into the high confidence design space, so we can get the percentage of batches which will be within the design space, which is quite high. But now, as I said, we have to look for another option because we cannot afford this new supplier. And the new one is to take advantage of the tools, of the properties of the PLS model. We know that we have different tools. One of them are the contribution plots. So it would be nice if we are able to take advantage of these contribution plots to provide to our supplier a way to improve. And for that, we use the centroid states and the variability states, as we will see. In the centroid state, we see that the centroid is outside the ideal centroid of the high confidence space. So it would be nice if we are able to provide some pieces of advice to our supplier to say, okay, if you are able to do that, you will be able to move your centroid from here to there, from the current point to the ideal one. And we only have to use a contribution plot from the diamond to the green point. And if we increase and decrease the mean of these variables, respecting the correlation structure from the past, we will be able to move from the current centroid to the ideal point, which is the centroid of the design space. And we were not able to do it, but we simulated this idea, and we were able to move in the simulated idea the centroid of the point from the current one to the ideal one. And now we see that we did it by steps to see, and now we see that we have a capacity index which is at least positive, higher than 0. Why? Because now the new centroid is within the high confidence design space. And we get, theoretically, this new ARMOS. We are able to do that. Would it be possible to improve even more this capacity? Yes, we can do it regarding the variability. For that, now we use again the contribution plots to see what variables are responsible of the critical direction, which has the minimum statistical distance. When we see this, when we see the variables which are responsible for this contribution, we know that reducing the variability of these variables, we will be able to reduce the variability of the ARMOS regarding this critical direction and improving the capacity. We did it by steps. So since we did it by steps, we had to correct these contribution plots. And at the end, we were able to increase even more the capacity from this value to almost 1, which is a nice value. We know that maybe our supplier is not able to modify the properties of the raw material because they cannot do it, but at least they are aware of the problem of the raw materials. And we also have been able to publish these ideas in ChemoLab. I'm sorry because this paper is not open access, but I guess we will be able to do it open access. I'm not sure, but we will try it. But at least you can find it in ChemoLab right now. And that's all. Thank you a lot for your attention. If you have any question, let me know. That's all.
Perfect. Thank you very much. I really like this. I followed Christiane Jäckle when she made her original work, and it's really nice to see how you have managed to develop this. I like it a lot.
Thank
Do
you.
we have any questions? Then feel free to ask them either in the chat, or if your microphone is proper, you can just ask it out loud. I do have one question.
Okay.
So from the fact that you're using the latent space,
Yes.
I guess you have better, let's say, better causality if you have a really bad process and you have huge variation in your raw material, because that gives you a bigger latent space, more room for optimizing.
Yeah.
If you have if your raw material doesn't vary at all, there's no possibility.
Yeah. Good point. Here we are able to find these causal movements in the latent space only because during the past there was a lot of variation, and it happens a lot in real processes. When you go to a real processes and you ask, "Have you done anything in this process?" They say no, everything is always the same for the raw material properties. But then we see that no, that change a lot, and we take advantage of these movements in the raw material variation and also in the process. Of course, if there is no movement, then we will not be able to find these causal ideas. We will be able to do it only if there were changes in the process and in the raw material properties.
Yeah. Yeah. So if you have a really good company, I mean, they do everything to try and make your methods not work. I mean, because they try to run at specified conditions. They try to make the raw material the same. So have you ever experienced that it was difficult to find meaningful causal models?
As you said, if there is no movement, no problem. But if there is a little bit of variations,
Yeah.
it's difficult to find this part. And for that reason, we can get this huge amount of uncertainty. For example, in the last one, we had so much uncertainty because there was only a little bit of variation. So it was difficult to find this causal information. But we can use it a little bit. For example,
Yeah.
if you want to optimize the process, you can find a better direction. Maybe the prediction will not be good enough, but doesn't matter. You know how to improve your process. So
Yeah.
sometimes it's more difficult than other times, but at the end, usually there is a little bit of information which is causal in the latent space, only a little bit, but
Yeah.
it's enough to take advantage of it. And if there is no information, of course, the only solution is first principles of run a design of experiments. But at least if you have been able to record data for years, look at the data. You can
Yeah.
do it easily. You have the data.
But sometimes maybe you can be allowed, normally not, but sometimes maybe you can be allowed to push the process. So you break some of the correlations. I
Yeah.
mean, I imagine that normally you cannot, but maybe there could be situations where you're allowed to do a little bit
Yeah.
to get more causality, so to speak.
Yeah, indeed, there is a project, and we are working right now in this project. When they realized that there was one Latent variable, well, a direction in the Latent variable, which
Yeah.
was related to the problem, but there were a lot of process variables aligned with this direction.
Yeah.
So they asked us, but which is the real one? And we answered, we don't know it. We know that the responsible is the Latent variable. If you want to know it, now you have to break this correlation structure of the original variables to check which is the best one, not the responsible of the problem. And they did it, and they found which was the first one. but they didn't have to do it using thousands of variables, only a few of them which were aligned with the latent variable aligned with the problem. So yes, sometimes you have to break the correlation structure to get more insight of the problem.
That's a nice one. I like that. By the way, I put a link to your company in the chat, so I would urge people to go there. And actually, I would also urge people to check the original papers, your papers for sure, but also the original papers by Christiane and her thesis.
Yeah,
If I don't know if that's available, but it's a very nice PhD thesis she wrote back.
very, very nice.
Yeah. Okay. Any other questions? I will make the webinar available on YouTube later on, so you can also come back and check here.
Perfect.
I like this very much. If there's not any other questions, then maybe I just want to say thank you so very much. I really, really enjoyed this. This is super nice work. Thanks.
Thank you.
Okay, and there's some other people thanking you in the chat.
And thank you so much for your attention. For me, it has been a pleasure to be here explaining these ideas.
And you did it well. I really like it. Thanks.
And if some of you have any question, feel free to contact me.
Right. Good. Yes.
Because I'm pretty sure if you try to read all these papers, the papers of Jekyll and McGregor and also other papers, a lot of questions will arise, so feel free to ask.
Yeah.